Hey everyone, I'm Shardul, and I'll be talking about a project that Clément, Adam, and I have been working on about verified firewalls. So first off, what does a firewall do? Um, from the outside, it might look like a firewall takes in some bytes from the network and returns a decision about whether to let those bytes through or not. But assuming we have something to convert between bytes and packets, we can phrase it such as making decisions on packets on the network. But that would just be a stateless decision. It wouldn't take into account what had happened so far, what packets you received in the past. So assuming you have some way to maintain and query a state, you can model a firewall as something that takes a state and a packet and updates the state and returns a decision about that packet. But notice that this updating of the state is actually going to be the same for every packet. It's just going to insert the new packet into your database of packets so far. So what the user would like to specify is just take a state and a packet and return a decision about that packet based on that state. And the updating is done in the background. Well, clearly this is not, while this is a good specification, it's not can't directly be an implementation because you might have to store an unlimited number of rows and many columns that are just irrelevant to the actual functioning of the firewall. So maybe you want to reduce this history somehow, or maybe you want to get rid of the history altogether and use a custom algorithm that just keeps track of some counters or some other variables to implement the behavior. Which is why we want to write refinements of the initial specification that is independent of the behavior, and then refine it into an optimized implementation that can be a realistic firewall. So this is the framework we're going to use overall. And why would we want to do this? Well, first off, verifying a firewall gives you an important security guarantee. And since firewalls are used in security where context, this is an important fact to be aware of. And it allows us to make a distinction between the behavioral specification of a firewall and its implementation. This distinction already exists in a lot of firewall tools like IP tables, and formalizing it gives us some expressive power. And we'd like to be able to extend our firewall DSL and add custom optimizations for new algorithms to implement the same behaviors. So doing this in Coq would let us write those extensions more naturally. So this motivates the project to build a verified compiler for a firewall DSL that is implementation agnostic. Now going into some more detail about how this works. Our firewall takes in a specification written in some notation and executes that specification by intercepting all the packets on the network. And here, let me point out that Narcissus is the first assumption we made that is an interface for converting between bytes and packets. This is a Coq library. And another Coq library, both of these are pre-existing work, by the way. Another Coq library is query structures that allows us to maintain and query a database of packets we've received so far. These are both part of the Fiat project that we'll be using as the general framework for doing this refinement. We also defined some notations to make writing these DSLs, writing these firewall behavior specifications easier. So this is our DSL. It mimics some parts of IP tables. You can write destination port, destination address queries, and a lot of the other flags that IP tables supports. And you can write history predicates, such as you can get the latest packet such that it satisfies some predicate. You can count in the last 1,000 ticks how many packets satisfy this predicate, and then compare that count to something. Here, the monadic notation with the bind and the standard if notation is provided by Fiat, which is a pre-existing specification library. But the notation for the firewall specific notation is what we've been working on. And now you can tie this notation together into an actual firewall spec. So this is an example. You might say, I want to count the number of packets in the last 1,000 ticks that are sent to the destination port 8 and from the source address, which is the source of the current packet. And if there are less than 10 of these, then accept the current packet, else drop it. And it gets plugged into Firewall, which is just the generic wrapper that does the state updating in the background and some other things. Okay, so what sort of optimizations can we do with this? An obvious one is column reduction. Not every firewall will need to access every single column, so we can just delete the ones that we don't need from the table of history that we're storing. And this is done completely via LTAC, and it generates a relation for refinement. It says that the database that stores the full packet is somehow related to the database that stores only some columns. It produces a proof that the firewall spec has the same behavior under this relation if you just use a projection of the packet instead of the full packet. And it applies these theorems to the firewall to refine it into one step closer to implementation. And we found that this is actually quite robust automation. It involved a fair amount of LTAC hacks, but we were able to get it working pretty well. The other way you can reduce history is by reducing rows. Like not every row will need to be accessed by the firewall in the future in the table. So after some point, you can just delete some rows without affecting the behavior of the firewall. And indeed, deciding which ones to delete is a pretty hard decision in general for an arbitrary firewall. But we were able to come up with some less hard heuristics and some proofs for those heuristics. So one example is pretty easy. If you just have a firewall like the example that has an explicit in last n ticks sort of notation, then you can delete anything that's older than n ticks. If you have a firewall that queries for existence of packets matching a certain criteria, it is sufficient to just keep one example, one certificate of that existence and delete the rest, or not need to store the rest. Or if you have a firewall that says, get the latest packet such that something, then you can just cache the latest packet and not have to store every single packet in history. And we have partial proofs for these, and some of them. So for the first one, we have complete proofs. Like in the next two, we have partial proofs. They're still in progress, and we found that they're hard to do in general, but for specific cases, not that hard. We talked before about being able to extend this DSL. So here's a concrete extension. Suppose we want to have a rate limiting firewall that says let no more than n packets through in k ticks. And the obvious way to do this is to just count the number of packets in the last k ticks and see if it's more or less than n. But there is an optimization we can do here, which is what iptables does actually. It's called a token bucket filter, and it acquires R tokens per tick, if that's the rate variable, up to a maximum of B tokens, which is the burst. And you can let a packet through by spending one token. So it's easy to see from this that a firewall that implements a token bucket filter will let no more than RK plus B packets through in k ticks. And this would allow us to replace a database of these storing the number of packets in the last k ticks with just a single counter that stores the number of tokens you have. So it's quite a significant efficiency gain. But we'd like to be able to prove that this refinement actually works. And this is also some ongoing proofs, which we've made some good progress on. In the future, I think we're looking, there's scope to do more of these row reduction heuristics like I talked about to support many different specifications. We are also thinking of doing downstream optimizations with Narcissus. So Narcissus is the library we use to convert between bytes and packets. It's a binary format encoder decoder. And if we already know which columns we will not be needing, maybe we can propagate that information down to Narcissus and not have to read those bytes off of the network to begin with. And we have some partial proofs and we have some automation. Like I mentioned, for column reduction, it's pretty robust automation, but the rest of it still needs to be tied together. And our high level goal would be to produce like a single user facing tactic that can be executed to compile any firewall. And some more notation engineering. The examples I showed are completely doable, but not yet fully implemented. And implementing them would have much more natural DSL. And we haven't thought yet about how this interacts with network topology and having multiple firewalls running on a network. So it's something to think about in the future. In conclusion, we have some interesting and exciting work about verifying firewalls. Are there any questions?
Thanks. Are there any questions, comments? Yes, Ben? Go on, please.
Hi. Very nice work. So have you done any performance measurement on the your firewalls? Have you compared it to, say, some, I guess, IP tables?
Not yet, because only recently were we actually able to get some of these row reduction heuristics working. I think without the row reduction heuristics, it has generally very poor performance because it stores an arbitrary amount of history. But now that we have these working, I think it's more realistic to try these performance benchmarks.
So related follow-up, if I can, what extraction mechanism are you going through right now? Are you just using CoqPL, using the standard extraction to ML, or have you looked at using, some of the work for doing verified extraction of imperative code?
As far as I'm aware, I think it's just extraction to OCaml.
Okay.
And some of the initial tests we ran were plugging it into like making an OCaml based, having some OCaml wrappers to make it an actual firewall that interacts with the network.
Okay, very cool. Thanks.
Thanks.
Okay, I thought I saw another person raise their hand in Zoom, but I missed that who it was. If there is any other question. All right, then otherwise we have a break now.
Okay.
And yeah, thanks for the talk. And we'll be back at 6 o'clock CET, so in 32